A cosine score of 0.8 is not a confidence level. Calibrate it on labeled pairs, so your embedding system stops turning near misses into accepted matches. You'll see how to connect the pieces into a workflow that traces trade-offs and chooses a similarity threshold to limit false matches. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Embeddings give you a compact signal about similarity, but they don't tell you whether a match is safe for your application. Teams reach for threshold calibration when a false match costs money or trust. For example, routing the wrong support answer or returning a privacy-sensitive snippet. A calibrated threshold turns raw model scores into an auditable rule you can rely on. The basic flow is straightforward. Label a small review set, score those pairs with your embedding model, and then pick the numeric cutoff that meets your safety target. You learn the cutoff from data instead of guessing. That one change often cuts false matches dramatically with only a little annotation work. We'll build a tiny, reproducible example. Map human labels to model similarity scores. Sweep possible cutoffs and pick a safe operating threshold. The point is a clear baseline you can rerun after any model update. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we create the labeled review set that keeps model scores next to judgment calls. This snippet creates a small, labeled review set for embedding similarity calibration. A cosine score alone does not say whether the pair is truly safe to accept, so labels keeps the human judgment next to each score. The pair's names are compact identifiers for real match and non-match examples, and scores represents the current embedding model's similarity output. Keeping all three lists aligned gives every later metric the same ordered inputs. The output confirms the review set size and shows one score that will become part of the threshold analysis. Now try applying a fixed cutoff and see what that naive decision looks like on the review set. This example evaluates what happens when a fixed similarity threshold is copied into this dataset. The code turns each value in scores into a Boolean decision with threshold, then counts TP, FP, and FN against the human labels. Precision is the important guardrail here, because false matches are accepted pairs that should have been rejected. Recall is still calculated, because lowering false matches usually means giving up some true matches. The output makes the cost visible. This copied cut accepts one non-match, so the score is not acting like calibrated confidence. If copying a cutoff looks unreliable, we can compute the whole precision recall trade-off and inspect every candidate threshold. This code uses scikit-learn's precision recall curve to evaluate every useful operating threshold. Instead of guessing one cutoff, the function takes labels and scores and returns aligned precision recall and threshold arrays. The final precision and recall point from scikit-learn has no matching threshold, so precision -1 and recall keep the rows comparable to cuts. The best row is selected for high precision first, then recall, then threshold. The output shows the threshold where this tiny review set reaches perfect measured precision. Often teams need a strict minimum precision. Filter the curve to meet that operational constraint, and then pick the most permissive threshold that still obeys it. This snippet filters the scikit-learn curve rows to thresholds that meet a minimum precision requirement. Teams usually care about a constraint, not a pretty curve. So min precision turns the plot into an operating rule. Among valid rows, max chooses the threshold with the highest recall, which keeps as many true matches as possible after the safety requirement is met. Raising min precision makes the system stricter and may reduce accepted. Lowering it can recover more matches, but may admit more false matches. The output shows the chosen cutoff accepts pairs without false matches in this review set. Finally, wrap calibration into a tiny comparison routine so you can track progress across models or runs. This example turns the calibration step into a tiny reproducible baseline for comparing embedding runs. The run scores dictionary holds two model outputs over the same label pairs, which keeps the evaluation fair. The calibrate function calls scikit-learn's precision recall curve, filters thresholds by the target precision, and returns the row with the best recall under that constraint. Report stores one calibrated result per run instead of copying a threshold from one model to another. The output names the run with stronger recall at the precision target and shows its own calibrated threshold. Mapping to real projects is straightforward. Replace the tiny review set with a few hundred labeled query passage pairs from your production logs. Keep the same pairs across runs and use the same min precision target when comparing models. That stability is what lets you meaningfully say one embedding model is better for this application. 3 short points to remember. Calibration means using labeled pairs to turn similarity scores into an operating cutoff. Use it when false matches have real cost or risk, and you need an auditable rule. One caution: a tiny review set can give noisy thresholds, so treat early cutoffs as provisional and track performance as you collect more labels. A practical next step is to scale the labeled set to 1,000 query passage pairs from your customer support corpus and rerun calibration while varying min precision to see the precision recall curve at production scale. That will show how much recall you lose for each safety level and point to whether you need a larger review set or a model change. If practical AI engineering helps you build safer systems, subscribe and watch the AI engineering videos.